still lining up for the Boeing 777X, even though it is nearly 7 years late. Now, I'm not talking about the usual "it's too big" argument. I'm talking about the hidden specs. For instance, did you know the A380 would be 15% more fuel efficient today if Airbus hadn't gambled on versions that were never ever built? There is a lot of engineering drama behind these two jets that rarely makes the headlines. You will want to see this. And hey, if you find this breakdown interesting, hit the subscribe button. It really helps a small creator like me to keep digging into these stories. Let's get into it. Infrastructure integration and geometric constraints. Firstly, let's start with those fancy wingtips on the 777 and look at what they really give to the airlines. The most significant operational hurdle for ultra-large aircraft is their interaction with existing airport geometry. The Airbus A380 was famously designed to fit within an 80-meter by 80-meter box, a constraint that dictated every major aerodynamic decision. The A380-800 is a permanent ICAO Code F Group 6 aircraft. This designation requires airports to provide runways with a minimum width of 60 meters and taxiways with a minimum width of 23 meters, along with significantly increased separation between parallel taxiways and runways to prevent wingtip collisions. The global adoption of the A380 necessitated billions of dollars in infrastructure upgrades, from strengthening bridges to installing specialized dual-level jet bridges. These costs acted as a massive entry barrier, effectively limiting the A380 to approximately 60 to 80 major global hubs. The Boeing 777-9 approaches this problem with a geometric dual identity. During flight, the wingtips are extended to a span of 71.8 meters, placing it in the same Code F category as the A380 for airside operations such as takeoff and landing. So what I mean? The 777X also require runways with a minimum width of 60 meters. However, upon exiting the runway, the outer 3.5 meters of each wing fold vertically, reducing the wingspan to 64.8 meters. This allows the 777-9 to operate as a Code E Group 5 aircraft on the ground, even loops as the Boeing 777-300ER and Airbus A350-1000. The 777-9 is notably longer than the A380, making it the longest passenger airliner ever produced. This length presents its own challenges for gate depths, but the folding wingtips eliminate the need for the lateral space expansions that the A380 demanded. Maneuverability and ground operations. The hidden complexity of ground maneuvering lies in the minimum turning radius and the 180-degree turn capability. The A380, despite its mass, achieves a surprisingly tight turn width of 50.91 meters, but only though the use of differential braking and asymmetric thrust, techniques that increase the tire wear and engine stress. The 777-9 requires a wider 59-meter pavement width for a standard U-turn without differential braking. A critical deal breaker for the A380 in ground operations is its turnaround time. Due to its double-deck configuration, the A380 requires specialized catering trucks and cleaning crews that can access both levels simultaneously. A typical long-haul turnaround of an A380 takes approximately 180 to 210 minutes, whereas the 777-9 is targeted to achieve turnarounds in 90 to 120 minutes, significantly improving aircraft utilization rates. Aerodynamic architecture and wing physics. The divergent philosophies of Airbus and Boeing are most apparent in their wing design. The A380 wing was over-engineered for a larger Dash 900 stretched variant that was never built, resulting in a wing area that is excessively large for the current Dash 800 model. Aspect ratio and induced drag penalties. The aspect ratio, AR, of a wing is defined as the square of the wingspan, B, divided by the wing area, S. For the A380, the AR is approximately 7.5 to 7.8, which is significantly lower than the 9.0 to 9.5 found on the newer twin jets like the 787 and A350. This low aspect ratio is a direct consequence of the 80-meter wingspan limit. To provide enough lift for a 575-ton aircraft within that span, engineers had to increase the wing chord, leading to a massive wing area of 845 meters squared. The aerodynamic penalty is severe. Induced drag due to weight, accounts for a 50% of total drag at cruise, which is 10% higher than it would be with an optimal 90-meter wingspan. The 777-9, by utilizing carbon fiber reinforced polymers CFRP and folding wingtips, achieves an aspect ratio of approximately 11.04. This slender wing generates lift much more efficiently and allowing for a higher cruise speed of Mach 85 compared to the A380's economical Mach 83. Wing loading and thrust-to-weight ratios. Wing loading, W divided by S, is a critical metric for takeoff performance and cruise efficiency. The A380 has a relatively low wing loading at MTOW due to its oversized wing, while the 777-9 operates at much higher pressures. The higher thrust-to-weight ratio of the 777-9, powered by the massive G9X engines, allows for superior climb gradients and better performance in hot and high conditions. The A380, while powerful, is hampered by its massive empty weight, which is nearly 10,000 kilograms heavier than the 777-9. Propulsion systems, G9X versus the quad-engine paradigm. The propulsion system is perhaps the single most important deal-breaker in the comparison. The A380 utilizes 4 engines, from either the Engine Alliance GP7200 or Rolls-Royce Trent 900. These engines represent late 1990s technology, which was quickly eclipsed by the G9X and Trent XWB generations. Thermodynamic efficiency and the GE9X. The G9X is the largest and most powerful commercial engine ever built, featuring a 134-inch fan and 27:1 compressor pressure ratio. It offers a 10% reduction in specific fuel consumption, SFC, compared to the G90-115B, and a nearly 20–25% improvement over the engines powering the A380. One hidden specification is the engine weight fraction. On the 777-9, the 2 G9X engines represent a smaller percentage of the MTOW than the 4 engines on the A380, despite the G9X's massive size. This is because the twin-engine configuration eliminates the need for 2 extra pylons, dual fuel lines, and complex quad-engine synchronization systems, engine maintenance cycles, and durability issues. A significant deal-breaker for the A380 is the sheer cost of engine maintenance. With 4 engines, an airline faces twice as many shop visits as a twin-engine operator. Engine maintenance for an A380 can reach $30,000 per flight hour, whereas a 777 operator typically spends $7,000 to $9,000 per hour on a 300ER, with the 777-9 expected to be slightly higher due to the complexity of the G9X. However, the G9X has faced its own challenges. In early 2026, a durability issue was identified regarding a seal in the high-pressure compressor. This issue led to a temporary flight test slowdown, with only 2 of 5 test aircraft flying in February 2026. While Boeing maintains this will not delay the first delivery in 2027, the long-term reliability of these ultra-high-pressure engines remains a concern for launch customers like Emirates and Lufthansa. Powerment dynamics, ACN, ACR, and CDF analysis. A hidden specification critical to airport planning is the impact of the aircraft's weight on the physical life of the runway. This is measured through the aircraft classification number, ACN, or the newer aircraft classification rating, ACR. The Powerment-friendly Giant. Despite its 575-ton mass, the A380 is famously Powerment-friendly. This is due to its 22-wheel landing gear configuration, which distributes the weight more broadly than the 14 wheels on the 777-9. The A380's main landing gear, MLG, consists of 2 6-wheel body gears and 2 4-wheel wing gears. The cumulative damage factor, CDF, analysis shows that the A380's wide gear track, 12.5 meters between wing gear axles, places the heaviest loads on the sections of the runway that are rarely used by other wide-body aircraft. Standard long-range jets, like the 777-300ER, have tracks between 10.6 and 11.9 meters. Consequently, the A380 contributes roughly 30% less to the peak powerment damage of a typical fleet mix than its gross weight would suggest. 777-9 powerment stress and ACR values. The Boeing 777-9, by constant, concentrates its 352-ton taxi weight onto 2 6-wheel trucks. To support this weight, the 777-9 uses higher tire pressures, 229 psi, than the A380, 218 psi. Higher tire pressure leads to higher vertical strain in the upper layers of the asphalt, potentially accelerating powerment cracking. The deal breaker here for small airports is that while the 777-9 fits in the gate, it may require runway strengthening if the subgrade is ultra-low, category D, as its ACR exceeds the PCN of many secondary airports. Cabin environment and psychoacoustics. Passenger experience is often marketed through luxury, but the true differentiators are noise levels, cabin altitude, and humidity, factors that directly influence jet lag and fatigue. The A380 noise advantage. The A380 remains the quietest large aircraft ever built. Measurements show that at cruise, the A380 mid-cabin noise level is approximately 68 dB, compared to 73 dB of the 777-300ER and roughly 70 to 71 dB for the 787 and A350. Because the decibel scale is logarithmic, a 5 dB difference represents a nearly 300% difference in sound intensity and 25 to 30% difference in perceived loudness. The A380's noise profile is also flatter, lacking the high-frequency hiss of airflow found in twin jets. This makes it the perfect aircraft for ultra-long-haul premium travelers. 777X atmospheric improvements. The 777X counters the A380's quietness with superior cabin atmosphere. By utilizing the 787's environmental control systems, the 777-9 maintains a cabin altitude of 6,000 feet, even at a flight level of 41,000 feet. The A380, designed with older aluminum alloys, typically maintains a cabin altitude of 7,000 to 8,000 feet. The 777X also features higher humidity levels and advanced filtration, which reduces the dry eye and dehydration symptoms common on the A380. Economic deal breakers. The cargo revenue gap. The most profound hidden specification that led to A380's commercial failure is the cargo-to-passenger ratio. Airlines generate a significant portion of their profit from belly cargo, which subsidizes the cost of the passenger flight. The A380 is a volume-limited aircraft. Its double-deck configuration uses up almost all the internal fuselage volume for passengers, leaving very little space for freight. The A380 provides approximately 133 cubic meters of cargo space, while the 777-9 provides a massive 230 cubic meters. On a route like Dubai to New York, JFK, an A380 burns roughly 65 tons more fuel than the 777 to carry potentially only 100 extra passengers. This makes the A380 economically unviable on any route where it cannot maintain a passenger load factor of at least 85%. The 777-9, with its high cargo capacity, can remain profitable even with a 60% passenger load, because the belly freight covers the fuel bill. The A380neo engineering realities and failure. The A380neo new engine option was a proposed upgrade meant to bridge the efficiency gap between the A380 and the 777X. However, the project was never launched due to a series of technical and financial death spirals. To achieve a 10 to 15% fuel burn reduction, the A380 requires modern engines like the Rolls-Royce Trent XWB or a D-rated GE9X. These engines have significantly larger fan diameters, 118 to 134 inches, than the original Trent 900, 116 inches. The heavier engines would increase the bending moment of the wing, requiring hundreds of kilograms of structural reinforcement. To maintain ground clearance for the larger nacelles, the landing gear would need to be lengthened, adding even more weight. Larger nacelles increase the wetted area and form drag, which would negate about 2 to 3% of the engine's efficiency gains. Airbus calculated that the OEW, operating empty weight, increase would be so significant that the NEO would only offer a 5 to 10% net improvement in fuel burn, not enough to justify the $3 billion development cost. Engine manufacturers like Rolls-Royce were unwilling to invest in a backspoke engine for the A380 when the total remaining order book was so small. Unlike the A320neo, which had thousands of orders, the A380 was a one-customer aircraft, Emirates. Developing an engine for a fleet of only 100, maybe 200 aircraft was commercially impossible for the OEMs, especially when they could focus on the A350 and 787 markets, where thousands of engines would be sold. System architectures and hidden specs. Beyond the airframe and engines, the internal systems of this aircraft represent two different eras of electrical and hydraulics engineering. Hydraulic pressure 5,000 psi versus 3,000 psi. The A380 was the first commercial aircraft to utilize a 5,000 psi, 35 megapascal hydraulic system, a significant jump for the industry standard 3,000 psi. High-pressure hydraulics allowed Airbus to use smaller, lighter actuators and thinner titanium piping to move the massive flight control surfaces. This saved approximately 1,000 kg in weight. The 777X maintains a hybrid approach, but relies more on electromechanical actuators for secondary systems, reducing the reliance on heavy hydraulic fluid lines throughout the cabin. Electrical generation, variable frequency versus constant speed. The A380 utilizes 450 kilowatt variable frequency generators. By allowing the generator frequency to vary with engine RPM, Airbus eliminated the heavy and maintenance-intensive constant speed drive (CSD) found on older jets. The 777X takes this further, utilizing a 787-style, more electric architecture, where the auxiliary power unit (APU) and main engines provide massive electrical reserves to power the environmental control systems (ECS) without the need for traditional bleed air from the engines. This no-bleed or low-bleed approach improves engine efficiency by 2–3% by not siphoning off high-pressure air from the cabin. Operational resilience, fact check and 2026 outlook. As of February 2026, the status of both programs has been affected by the global recovery and technical setbacks. The 777X program is currently 6 years behind its original schedule, with the first delivery to Lufthansa now expected in second quarter of 2027. The FAA and EASA have increased their oversight, requiring a phased type inspection authorization that has slowed progress. Despite this, the order book has remained resilient, with Emirates adding 65 more 777X units at the Dubai Air Show 2025, bringing their total commitment to 270 aircraft. The A380 has defined early retirement predictions. As of April 2024, there were 189 aircraft in service with 10 operators. By 2026, the global fleet valuation has actually increased by 2.8%, as airlines realize they cannot meet post-pandemic demand without the Super Jumbo's capacity. Emirates plans to fly the A380 until 2040, investing in massive cabin refurbishments to keep the fleet modern while waiting for the 777X. Maintenance and life cycle costs. Maintenance costs are the ultimate hidden spec that determines the long-term viability of an airframe. The deal breaker for many A380 operators like Air France and Thai Airways was the sunk cost of point-to-point operations. By the time an A380 is turned around and ready to fly, the airline has already spent nearly $500,000 in fuel, staff and landing fees. On a twin jet, these fixed costs are significantly lower, providing the airline with more exit liquidity if a route underperforms. Now share your thoughts in the comments. Maybe you know more interesting hidden specs. I'll be really interested to hear your opinion. Don't forget to like and subscribe. But now let's meet in some of these videos. See you! Take a close look at this image. To most people, this looks like a pilot's worst nightmare. But to an engineer, this is a masterpiece. This is a triumph of design. On September 3, 2025, something incredible happened. In a single day, two different business jets, Gulfstream G150 in Chicago and Challenger 300 in Boca Raton overran the runway. Both planes were heavy, moving fast and running out of pavement. Both should have ended up in a highway or a building. But they didn't! They stopped safely, the passengers walked away, and the planes didn't even catch fire. They were saved by a technology that hides in plain sight at the end of the runway, EMAS, the Engineered Materials Arresting System. Today we are going to look at the hidden engineering that keeps you alive when a landing goes wrong. But first hit the like and subscribe button. This simple action is vital for me. Thank you very much. The science of soft concrete. So what actually is a EMAS? If you look at the end of a runway, it looks like a normal extension of the pavement. But it is not. It is a trap. The secret lies in the material itself. This is made of cellular cement, also known as format concrete. Imagine a block of concrete, but instead of being solid, it is filled with millions of tiny air bubbles, like a honeycomb. The engineering brilliance here is not about strength, it is about weakness. Normal concrete, the kind you walk on, is incredibly strong. It can withstand pressure of 4,000 psi, pounds per square inch. If a plane hits that, the landing gear snaps. But EMAS blocks are engineered to be weak. They have a specific crush strength of only 30 to 50 psi. Compare 4,000 to 30 or 50. This number is very precise. It is strong enough to support the weight of a fire truck or a maintenance vehicle without braking. But the moment the thin tires of a heavy jet hit the blocks, the material gives up. It crushes instantly. Part 2. The physics of arrestment. When a plane enters the EMAS bed, the tires slice through the material like a knife through dry foam. The wheels sink into the bed. This creates drag. The material absorbs the kinetic energy of the moving aircraft and converts it into mechanical crushing work. It acts like a giant brake pad made of stone. The system is designed to stop a critical aircraft, usually a heavy jet, entering the bed at speeds up to 70 knots, about 130 km per hour. And the most important part, it does this smoothly. The bed is usually built as a ramp. It starts shallow, maybe just a few inches deep, and gets deeper towards the end, sometimes up to 30 inches. This slows the plane down progressively, so the passengers don't feel a violent impact. Part 3. The problem when space runs out. Why do we need this expensive technology? Why not just make the runway longer? The Federal Aviation Administration, FAA, has a strict rule. Every runway must have a safety net. This is called the RSA, or Runway Safety Area. The standard RSA must extend 1,000 feet, about 300 meters, beyond the end of the runway. This is a flat, empty, grassy area where a plane can roll safely if it fails to stop. But look at the map. Many airports are built 50 or 60 years ago. Since then, cities have grown around them. Some airports end at the edge of a cliff. Others end at a busy 6-lane highway. Some, like LaGuardia or San Francisco, end directly in the ocean. And these places you cannot just add land. It is physically impossible or financially ruinous. Part 4. The economic solution. This brings us to the economics of safety. Let's look at the real example. Greenville Downtown Airport. They had a steep drop-off at the end of their runway. To build a traditional 1,000-foot safety area, they would have to build a massive earth embankment. The estimated cost was $16 million. Instead, they installed an EMAS. Because the material stops planes so efficiently, you don't need 1,000 feet. You can do the same job in a much shorter distance. The cost of the EMAS? $1.8 million. Compare one more time. 1.8 to $16 million. It saved the airport $14 million. And it provides the exact same level of safety. Part 5. A history of safes. This is not theoretical. This technology has a proven record called tombstone technology. Solution born from past accidents, but now saving lives. Since the first successful safe of a Saab 340 at JFK Airport in 1999, EMAS has stopped dozens of aircraft. In Charleston, West Virginia, a CRJ-200 regional jet aborted its takeoff. The runway ended at a steep mountainside. The EMAS caught it just in time. In Tattleboro, a Gulfstream 4 was stopped before it could cross a busy highway. And of course, the events of September 2025. 2 jets, 2 wet runways, 2 potential tragedies, 0 fatalities. But EMAS is only the last resort. Ideally, we never want to use it. To understand how we keep planes on the runway, we have to look deeper. We need to look at the invisible battle happening between the tire and the pavement. And it all starts with a formula from NASA. Part 6. The physics of touchdown. The most dangerous enemy of a landing aircraft is not wind, and it is not pilot error. It is water. When a plane lands, it is not just rolling. It is fighting a hydrodynamic battle. If the water on the runway is deeper than just 3 millimeters, 0.1 inches, a phenomenon called dynamic hydroplaning begins. The water builds up pressure in front of the moving tire. It forms a wedge that physically lifts the rubber off the concrete. In the 1960s, engineers at NASA's Langley Research Center, they found that the speed at which you lose control depends on only one variable. It doesn't matter how heavy the airplane is. It doesn't matter how skilled the pilot is. The only thing that matters is the tire pressure. They created a formula that is still the Bible of aviation safety. Vp equals 9 square root of P. Here, Vp is the hydroplaning speed in knots, and P is the tire pressure in psi. Let's look at the numbers. A commercial airliner like a Boeing 777 has very high tire pressure, around 200 psi. According to the formula, it will hydroplane at about 127 knots. That is fast, but it is usually below the landing speed, so the risk is manageable. Its tires are only inflated to 36 psi. The formula tells us it will lose control at just 54 knots. This means a small plane is actually more likely to hydroplane than a massive jet. Part 7. Reverted rubber, the steam seal. But there is a type of hydroplaning that is even scarier. It is called reverted rubber hydroplaning. This happens when a pilot locks the wheels on a wet runway. The friction generates insane heat. This heat boils the water trapped under the tire, turning it into a high-pressure stream. The steam gets so hot that it melts the rubber on the tire, rewetting it back to its raw, sticky, uncured state. The result is a disaster. The melted rubber forms a seal around the steam, creating a cushion. The aircraft is now literally riding on a pocket of superheated stream. Investigators know when this happens. They find telltale signs on the runway. White marks that look like the pavement has been stream cleaned, elongated patches of melted rubber. Part 8. Engineering the surface. Grooving. So how do engineers fight this? We cannot stop it from raining, so we change the ground itself. If you look closely at the major runway, you will see it is not smooth. This is called grooving. Engineers cut thousands of channels across the runway. The FAA has a very strict standard for this geometry. The groovers are 1/4 inch 6 mm deep. They are 1/4 inch 6 mm wide. And they are spaced exactly 1.5 inches 38 mm apart. These tiny channels give the water an escape route. It flows into the groovers and drains away, allowing the tire to grip the length, the high points between the cuts. This simple geometric pattern can increase friction on wet pavement by up to 300%. But maintaining this is a nightmare. Every time a heavy jet lands, the tires spin up from 0 to 140 knots in an instant. This abrasion rubs off about 1.5 to 2 pounds of rubber onto the runway. Over time, this rubber fills the groovers. If 40% of the groovers are blocked, the runway becomes dangerous. That is when maintenance crews come in with ultra-high pressure water blasters, shooting water at 40,000 psi to strip the rubber off without destroying the concrete. Part 9. The layer cake. Hidden structure. Now let's go deeper. Literally. Passengers think a runway is just a road, but a highway is designed for trucks. A runway has to survive a 300-ton machine slamming into it at 250 km per hour. If you sliced a runway in half, you would see it is a massive engineering layer cake, more than 2.5 meters thick. Look at the cross-section. At the very top you have the surface course. This is the asphalt or concrete we see. Below that is the base course, often made of cement-treated aggregate. Then the subbase, and finally the subgrade, the native soil. In major international airports, the top layer alone can be 22 inches, 56 centimeters, of solid Portland cement concrete. This is thicker than the walls of a military bunker. This structure is designed to distribute the massive points of load of a single wheel. If the layers were not there, the landing gear would punch through the pavement and sink into the dirt. Part 10. The evolution of design. For decades, engineers designed these layers using old charts and tables called the ACN-PCN system. It was based on empirical data from the 1950s. But modern aircraft gear is too complex for simple charts. In July 2020, the aviation world switched to a new standard, ACR-PCR. This is a mechanic approach. Engineers now use computer simulations called layered elastic analysis. They model the runway as a multi-layered elastic system in a digital environment. They can predict exactly how the pavement will bend and rebound under every single wheel of an Airbus A380. Part 11. The chemistry of asphalt. Finally, even the asphalt itself is high-tech chemistry. It is not just tar and rocks. Engineers use a performance grading (PG) system to design the binder. In a hot climate like Dubai, they might use PG 7622. The 76 means the asphalt won't melt or rot until it reaches 76 degrees Celsius. To achieve this, they modify the bitumen with polymers like CBS. It is basically turns the road into a very stiff rubber band. In a cold climate like Alaska, they use PG 5234. The 34 means it stays flexible down to minus 34 degrees Celsius, so it won't crack in the winter. We built the ground to match the sky, but even the best pavement is useless if the pilot can't see where to land. That is where the engineering of flight comes in. Part 12. Tombstone technology. There is a dark saying in aviation: regulations are written in blood. Engineers call this tombstone technology. It means that many of the safety features we see today were invented only after a specific disaster. Take the tragedy of American Airlines Flight 1420. In 1999, an MD-82 jet overran the runway in Little Rock, Arkansas. It didn't stop in the grass. It collided with a rigid steel walkway that supported the approach lights. The steel structure didn't break. Instead, it tore the aircraft apart. That accident forced a critical change in engineering. It is called fungibility. Today, strict FAA rules state that any object located in the runway safety area, whether it is a light pole, a sign, or a navigation antenna, must be fungible. This means it is engineered to be brittle. It is strong enough to stand up to a storm, but designed to snap, buckle, or yield instantly if an aircraft hits it. The object must die, so the passengers can live. We see this pattern everywhere. After the collision of two Boeing 747s in Tenerife in 1977, airports were required to install ground radar, ASDE, to see through fog. After the crash of Singapore Airlines Flight 006 in 2000, where a pilot turned onto a closed runway by mistake, lighting standards changed. Now taxiway lights must be physically locked out so they never lead a pilot to a closed runway. Part 13. The language of light. But the best safety system is one that prevents the accident before it happens. This brings us to engineering of light. When a pilot approaches a runway, they don't just guess their altitude. They look for a box of 4 lights on the left side of the runway, the precision approach patch indicator. It looks simple, but the optics are incredibly precise. The system is calibrated to define a perfect 3-degree glide path. Each light unit projects a split beam. The top half is white and the bottom half is red. The transition between the two colors is razor sharp, less than 3 minutes of arc. This creates a simple code for the pilot. 4 white lights, you are too high, more than 3.5 degrees. 4 red lights, you are too low, less than 2.5 degrees. This is dangerous, you might hit terrain. 2 red and 2 white, you are perfectly on the 3-degree path. Part 14. The runway is talking. Once the wheel touches the ground, the engineering shifts from guidance to distance. At night, a pilot cannot easily see how much pavement is left, so the runway talks to them using color codes mandated by the FAA. The centerline lights, the lights running down the middle of the runway, are not just white. When there are 3,000 feet remaining, the lights start alternating red and white. This is the first warning. In the final 1,000 feet, the center line turns solid red. This tells the pilot, you are running out of space. Stop now. Even the edge of lights participate. In the last 2,000 feet, or half the runway length, the white edge lights turn yellow. This creates a visual caution zone for the pilots. Now I'm serious. Which part of this hidden engineering surprised you the most? Was it the soft concrete of EMAS, or the fact that NASA formulas control your landing? Write your thoughts below, I read every comment. If you learned something new today, hitting the like and subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you in the sky! Do you know how airline CEO choose between B787 or A350? It is pretty obvious that they don't just compare how many passengers plane can carry or how far they can go. Even savings on fuel are not always a deal breaker. So today I won't do this. Instead, let's look at the exact hidden specs which look really insignificant to an ordinary aviation fan, but they make a huge difference to the airline CEO. But first, hit the like and subscribe button. This is a super simple action, but I really need your support. For me, it is vital. Thank you. Chapter 1. The strategic bet. Frequency versus capacity. Let me start from the explanation why this comparison even makes sense. Some can say that the Airbus A380 is actually closer to the Boeing 777 than to the 787. And they will be right, exactly in the case of the A350-1000 version. But others can argue that A350-900 is not a direct competitor to the 777, and especially 777-9. It is much closer to the Boeing 787-9 or 10, and they will be also right. But from the third point of view, the A330neo is closer to the Boeing 787 than the A350, and this also makes sense. So what I wanna say is that manufacturers have the right version of the airplane to compete in the majority of niches, but none of their models are the pure rivals in every version. All of these comparisons make sense, but in different videos. If you wanna see some of them, let me know in the comments below. Anyway, let's get back to our main heroes, the Airbus A350 and the Boeing B787. Look, here is the thing. When Boeing sat down to design the 787, they were literally betting the house on a concept called fragmentation. They sort of predicted that era of massive hubs was ending. They figured passengers didn't want to connect in huge airports anymore. They wanted to go straight up to point, like from Osaka directly to Sanjus. To make that work, you need a plane that is cheap to run even if it is not totally full. And this brings us to the first massive difference. To be honest, for the 787, the most critical metric is trip cost. Basically, the 787 is lighter and smaller. It is optimized for around 290 passengers. It is designed to minimize risk. I mean, if you can only sell 200 tickets, on a big plane you are losing money. But on a 787, you might actually break even. So it's kind of a safety net for the airline's bank account. On the other hand, Airbus was playing a different game. Seriously, the A350XWB was a direct attack on the Boeing 777 market. They focused on hub-to-hub routes with high demand. Mind you, the A350-900 is bigger. It holds about 325 passengers, which is like 30 or 40 more seats than the Dreamliner. Fair enough, the A350 costs more to fly than a 787. It burns more fuel per trip, no doubt. But here is the trick. If you can fill those extra seats, the A350 actually prints more money per passenger. It is all about CASM, cost per available seat mile. It is a volume game. You know what I mean. And listen, this leads to a hidden spec that almost nobody talks about, but CEOs check it immediately. Maximum takeoff weight, or MTOW. The 787-9 is sitting at around 254 tons. The A350-900, it is a beast at 283 tons. For real, that is massive. Well, airports charge you landing fees based on weight. So if you buy the heavy A350 and fly it half empty, you are literally burning cash on fees and fuel for structure you don't need. That's a nightmare. But at the end of the day, if you have a slot-constrained airport like London Heathrow, where you can't just add another flight, you need that extra capacity. In that case, the A350 is probably the better option. Chapter 2. The barrel versus the panel. The repair nightmare. Okay, listen, let's talk about what these things are actually made of. We all know that both planes are pretty much plastic. Well, carbon fiber reinforced polymer, or CFRP to be precise. But the way they build them, it is totally different. And this difference is low-key terrifying for the maintenance managers. Look, Boeing went full sci-fi with the 787. They decided to make the fuselage sections as one giant solid piece. It's called a one-piece barrel. They literally spin carbon fiber tape around a huge mold. No rivets, no joints, just one smooth tube. It saves like 20% weight compared to aluminum, which is huge. But here is the thing. What happens when a catering truck accidentally hits the side of the plane at the airport? It happens, you know? If you dent a traditional aluminum plane, you just rivet a patch on it. But on a 787, it is a nightmare. Seriously. You can't just cut a hole and plug it. You have to do a process called scarfing. You have to sand down the damaged layers circle by circle, apply a patch, put it under a vacuum, and heat it with a special oven right there on a tarmac. It is super complex work. I mean, if the damage is bad enough, your shiny 787 could be stuck on the ground for weeks. For a CEO, having a plane that can't fly is straight up losing money. Now look at Airbus. They saw what Boeing was doing and said, I don't think so. For the A380, they choose a panel-on-frame approach. It is basically 4 huge carbon panels, top, bottom and 2 sides, bolted onto a carbon frame. It sounds less cool, I guess, but it is way smarter for repairs. If that same truck hits the side of an A380, it is fair enough to say the repair is much more straightforward. You are dealing with the panel, not the structural integrity of the entire tube. It is kind of like Legos compared to Boeing's pottery. Chapter 3. The heart and lungs. Engines and the bleed war. Look, the fuselage is cool and stuff, but the real revolution is happening inside the systems. And honestly, this is why Boeing and Airbus went in totally opposite directions. It is called the bleed air war. Basically, on a normal plane, the engines provide thrust, but they also do something else. The plane literally steals hot, high-pressure air from the engine compressors to run the air conditioning, pressurize the cabin and de-ice the wings. This is called bleed air. Well, for the 787, Boeing said, we are done with that. The 787 is the first commercial, more electric aircraft. They straight up removed the heavy pneumatic ducts and valves. Instead, they installed massive electrical generators on the engines. I mean, we are talking about 1 megawatt of power generation on board. That is enough to power a small village, no doubt. Well, bleeding air from the engine kills efficiency. By going electric, Boeing saves like 3% on fuel. That is huge. But here is the thing. This makes the 787 electrical system incredibly complex. You remember the early battery fires? That was the price of innovation. And for mechanics, fixing high voltage systems is high-key dangerous if you aren't careful. Airbus? They looked at this and said, too risky. So the A350 actually kept the traditional pneumatic system. It still uses bleed air. It is conservative, I guess, but it is super reliable. Mechanics know how to fix it because it is pretty much the same technology they have seen for decades. And then there are the engines themselves. The A350 is exclusive to the Rolls-Royce Trent XWB. And to be honest, this engine is a masterpiece. It uses a 3-shaft design, which is unique to Rolls-Royce. It allows the compressor to spin at crazy 50-to-1 pressure ratio. It's legit the most efficient large aero engine flying today. And unlike the Trent 1000 on the Boeing 787, which had those nightmare issues with cracking blades, the XWB has been rock solid. On the other hand, the 787 gives you a choice, and most airlines pick the General Electric GE/X. Why? Because it uses composite fan blades. They are carbon fiber, not titanium. This makes the engine lighter by like 400 or 500 kilograms. That is half a ton of free cargo you can carry, literally. Or $2,000–5,000 of extra revenue every flight. So what does this mean for the numbers? If you look at the specific fuel consumption per passenger, the 787-9 sits around 2.31 liters per 100 kilometers. The A350-900 is around 2.39 liters. It looks like a small difference or whatever, but over the life of a plane, the 787 is just slightly more efficient at sipping fuel per trip. But remember, the A350 carries more people, so it balances out. Chapter 4. The Office, Flight Options and Philosophy. Honestly, this is where the difference between Boeing and Airbus stops being about engineering and becomes almost religious. Here's the thing. The philosophy of how you fly these birds is totally opposite. Airbus uses something called hard protections. On the A350, the computer is literally the boss. I mean, if you can pull the side stick all the way back, and the computer will just say, no, it won't let you bank past 67 degrees, it won't let you stall, it keeps you inside the safe envelope period. Boeing? Well, they have a different view. The 787 uses soft protections. The computer will warn you, it will put resistance on the yoke, like fighting you back, but at the end of the day, if you pull hard enough, the plane will let you do whatever you want, even if it breaks the plane. The pilot has the final word. So which is better? I guess it depends on who you ask. But for the CEO, there is another acronym that matters way more than flight philosophy: Cross-Crew Qualification. Listen, training pilots is expensive. Low-key, it is one of the biggest costs for an airline. If you already have a fleet of A330s, which tons of airlines do, retaining a pilot to fly the A350 takes just 8 days. Seriously, 8 days. It's called a reduced type rating. They can even fly both planes at the same time. For the Boeing 787, even if you are coming from the 777, the transition takes like 15 to 20 days. It is nearly double the time. Mind you, paying for hotels, simulators and instructors for an extra 2 weeks for hundreds of pilots, that is literally millions of dollars in savings for Airbus operators. And then there is the tech right in front of your face. If you jump into a 787, you will see the dual head-up displays, HUDs, as a standard equipment. It looks like a fighter jet. You can land in fog without ever looking down. It's pretty much the coolest toy in the industry. The A350? Well, it focuses on screens. Massive 15-inch displays. It feels like a flying IT center. HUDs are usually just an option, however the popular one. Chapter 5. The passenger experience. The wits lie. Now let's go back to the cabin. Honestly, this is where the marketing brochures usually hide the ugly truth. I call it the wits lie. You know, the A350 is called XWB. That stands for extra wide body. Let's look at the raw numbers. The cabin width of the A350 is 5.61 meters. The Boeing 787, it is 5.49 meters. So the difference is basically 12 centimeters. You might think, 12 centimeters? Who cares? That's like a length of a phone. But here is the thing. In the world of economy class, 12 centimeters changes everything. See, when Boeing designed the 787, they kind of envisioned it with 2-for-2 configuration. In that layout, it is super comfy. But airlines love money, right? So pretty much every major airline squeezed a 9th seat in there. The seats on a 787 are typically 17 inches wide. Seriously, if you are a normal-sized human, your shoulders will be touching the person next to you. It is tight. Airbus, on the other hand, designed the A350 for 333 seats from the day one. That extra cabin width means you get a standard 18-inch seat. Look, 1 inch doesn't sound like much, but on a 14-hour flight? It is the difference between sleeping and suffering. If you value your personal space, you literally want the Airbus. Now regarding the air you breathe, it is a draw. Because both planes use composite fuselages, they can handle higher pressure. So instead of the typical 8,000 feet cabin altitude, both the 787 and A350 keep it around 6,000 feet. This means more oxygen in your blood and fewer headaches. Totally a win for everyone. By the way, we have to talk about the windows. The 787 has those famous electronic dimmers, no physical shades. It looks futuristic and stuff, but they don't block 100% of the light. If the sun is shining directly on your window, it still gets sort of bright and hot. The A350 is stuck with traditional pull-down shades. It is old school, fair enough, but when you close it, it is actually dark. However, in the case of Airbus, some airlines have also chosen an option of electronic dimmers. Chapter 6. The belly. Cargo and liquidity. Okay, passengers pay the bills, but cargo. Cargo is pure profit. Honestly, this is a hidden battleground where the A350 high-key shines. If you look at the spec sheet for the standard versions, the 787-9 and the A350-900, they both fill exactly 36 cargo containers, LD3s. So it looks like a tie, right? Well, not exactly, because there is a trap called payload range. Here's the thing. On a medium flight, sure, both planes can take a full load of passengers and a full belly of cargo. But what happens when you fly super long distances, like San Francisco to Singapore? On those ultra-long range routes, the Boeing 787 hits its maximum takeoff weight limit faster. It has to leave cargo behind to carry enough fuel. The A350 with that massive 283-ton weight limit we talked about earlier, it keeps lifting. Actually, on those extreme routes, the A350 can carry like 5 tons more cargo than the 787. Think about it. 5 tons of high-priority freight, iPhones, pharmaceuticals, whatever. That is thousands of dollars per flight. For a CEO, that extra cargo revenue basically pays for the fuel and the crew. It is literally free money. But wait a minute, there is one final financial spec, the asset value. To be honest, the 787 is the liquid king of widebodies. Boeing has built over 1,100 of them. They are everywhere. It is super easy to buy or sell one quickly. But here is the thing. Boeing Common isn't always best for the bank account. If you look at the market numbers for 2025, the A350 actually wins on value. An A350-900 brings in like 1.25 million a month in lease payments. The 787-9, it is sitting lower at around 1.10 million. So even though the A350 costs more to buy, it holds its value better. Analysts say it has better residual value stability, because the market isn't flooded with them yet, and demand is high. Basically, for a CEO, the 787 is a liquid asset you can flip fast, but the A350 is a stronger asset that generates more cash every single month. Conclusion and verdict. Look, theory is cool, but let's see how this actually plays on the real world. Why do airlines really choose one over the another? Take Delta Airlines. They operate both. Actually, it makes perfect sense. They use the A350-900 as their flagship for heavy routes across the Pacific. But for routes that are a bit thinner, like New York to London, the A350 is too big and heavy. So they ordered the Boeing 787-10. It fits perfectly in the middle. They literally use the right tool for the right job. Then look at Singapore Airlines. They fly the longest flight in the world, Singapore to New York, 18 hours. They choose the A350-900 ULR. Why? Because, as we discussed in Chapter 6, The 787 hits a weight limit on those extreme ranges. The A350's fuel system allowed them to fly the distance and still make money. No doubt, Airbus won that niche. And finally, Emirates. This is where it gets spicy. They ordered 50 A350-900. Why? Because the Rolls-Royce XWB engine proved it can handle the desert heat and sand. Mind you, they are still fighting with Rolls-Royce about the bigger engines for the A350-1000, complaining about maintenance costs. But for the 900, they trusted more than the early engines on the 787. So in the desert, reliability was the deal breaker. So here is the final verdict. Choose the Boeing 787 if you want to open new routes between smaller cities, point to point. You want the lowest possible cost per trip to minimize risk. You need a liquid asset that is easily to buy and sell. Choose the Airbus A380 if you are replacing big Boeing 777s and fly between major hubs. You have a bunch of A330 pilots and want to save millions on training. You need that extra cargo capacity on super long flights. You want the passengers to love you for those 18-inch seats. At the end of the day, it is not about which plane is better. The 787 is a surgeon's scalpel, precise and efficient. The A350 is a Slitge hammer, powerful and capable. Anyway, both work if you know what you are doing. Which one would you choose if it was your money? Let me know in the comments below. And if you enjoyed this deep dive, please hit that like button. It really helps the channel. Don't forget to sub. See you in the next one. Have you ever lost your house keys? It happens to everyone. Now imagine losing something much bigger. Imagine the world losing 4 massive Boeing 777 airplanes. Each one weighs 200 tons. In December 2022, something incredible happened. Several of these jets, which used to fly for Singapore Airlines, took off from storage airports in Uzbekistan and Cambodia. They climbed into the sky and then they simply dissolved into thin air. But they didn't crash. There was no emergency. Instead, these American-made giants secretly landed in Tehran. How is this possible? How did Mahan Air, the most sanctioned airline in the world, manage to smuggle 4 modern airliners right under the nose of the CIA? Let's find out. But first, hit the like and subscribe button. This simple action is vital for me. Thank you very much. Chapter 1. The Madagascar Gambit. So, how do you legally buy a plane if the world forbids you from buying one? The answer is simple. You don't use your own name. You use a shell company. This is a fake business set up in places like UAE or Gambia. On paper, it looks like a normal company buying a plane for travel. But in reality, it is just a mask. But buying the plane is only step 1. You also need to register it. For these Boeings, the smugglers used a clever trick. They registered the planes with the code 5R, which belongs to Madagascar. Why Madagascar? Because the aviation control there is weak, and regulations are easy to bypass. They created a fake airline that claimed it would fly charter flights for tourists. It was the perfect cover. Then came the escape. The planes flight a normal flight plan, for example flying towards Uzbekistan. They took off and everything looked standard. But then, they reached a specific point in the sky, usually over Afghanistan. At this exact moment, the pilot turned off the transponder, the device that tracks the plane. The dot disappeared from the radar screens. The plane became a ghost. The pilot changed course and flew directly into Iran. This is known as the Blue Service method. It is the exact same trick they used to smuggle Airbus A380s before. It is risky, but it works. Chapter 2. The Technical Detectives. Why did they choose these specific planes? Why is the Boeing 777-200ER? These were not new jets. They were retired planes from Singapore Airlines and Knox Scoot. For a long time, they were just sitting in the desert, like the famous airplane graveyard in Alice Springs, gathering dust and waiting to be scrapped. Then they were moved to Asia. But the real secret lies under the wings. The engines. These planes are powered by the Rolls-Royce Trent 800. This is the critical detail. Most modern Boeing 777s use G90 engines made by General Electric. The problem for Iran is that General Electric is an American company that watches everything. They track every screw and every sensor. It is a nightmare for smugglers to get parts for them. Rolls-Royce is British. While they are also under sanctions, the black market for their parts is slightly softer. Iran may already have old connections to get what they need. There is also a simple economic reason. Nobody else wants these planes. The Trent 800 is an older, thirsty engine. It burns a lot of fuel compared to modern jets. On the legal market, these planes are almost worthless. This makes them incredibly cheap to buy with cash. For a smuggler, they were the perfect bargain. Chapter 3. Cannibalism and donor planes. You might wonder, why did they steal 4 or 5 planes? Maintaining just one huge Boeing is already a headache under sanctions. Maintaining a whole fleet seems impossible. The strategy is dark but smart. In the aviation world, it's called cannibalism. Here's how it works. Iran buys 4 planes, but they only plan to fly 2 of them. The other 2? They are doomed. They become organ donors. When a fuel pump breaks or a computer fails on the flying plane, they don't order a new part from America. They just walk to the hangar, rip the part out of the grounded plane, and install it on the active one. It is much cheaper and more reliable than trying to find smuggled spare parts on the black market every week. But hardware is only half the battle. These planes have no access to official Boeing software updates. There are no service manuals or technical support. If a warning light turns on, you can't call customer service. This has forced Iranian technicians to adapt. Over the years, they have become masters of reverse engineering. They have learned to fix complex American technology without instructions, keeping these metal birds in the sky long after they shouldn't have been grounded. Chapter 4. Geopolitics and the powerlessness of the West. This brings up to the big question: where was the United States? The US had the most powerful military and intelligence network in the world. Why didn't they shoot these planes down or arrest the pilots? The answer is a frustrating legal dialogue. You cannot simply arrest a plane while it is flying 30,000 feet in the air, especially over neutral or friendly territory. Until the wheels touch the ground in a country that follows US laws, American authorities are powerless. They likely watched the shaft happen on their screens, but they couldn't do nothing to stop it. So what is the future of the stolen giants? They cannot fly to London, Paris or Berlin. If one of these stolen 777s lands in Europe or North America, it will be seized immediately by lawyers and authorities. Instead, these planes will fly a limited network. You will see them on domestic routes inside Iran or flying to friendly hubs like Moscow, Beijing, Istanbul and maybe Dubai. They are big birds in a small cage. There is a deep irony here. These are American machines, built by American workers in Seattle. Now they are the pride of a regime that considers the US as an enemy. It is a strange reality. A country that burns American flags on the streets is desperate to fly in American planes in the sky. Conclusion: the price of risk. So Iran did it. They showed the world a masterclass of bypassing sanctions. They tricked the regulators and they got their prize. But this is a victory with a very heavy price. Ask yourself this honestly. Would you feel safe on that seat? We are talking about a plane that is being kept alive by cannibalizing other aircraft. It has not had an official technical inspection for years. It is flying without manufacturer's safety net. It is basically a Frankenstein monster of the skies. Ultimately, this story is not just about aviation enthusiasts or secret agents. It is a story about survival. It shows us exactly how far a government will go to keep its economy moving. Every rule in the book. Now I want to turn the question to you. Knowing the history of these ghost planes, knowing they are fixed with scavenged parts, would you buy a ticket? Write in the comments below, would you risk flying on this Mahan Air 777? If you learned something new today, hitting the subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you next time. Look at this airplane. This is the Embraer E2, also known as the Profit Hunter. With its tack shark livery, it looks like the future of aviation. It is the quietest and the most fuel-efficient narrow-body aircraft in the sky. And for us, the passengers, it is a dream. Why? Because there are no middle seats. It's a 2+2 configuration. No more fighting for an armrest with a stranger. On paper, this plane is a masterpiece of Brazilian engineering. It was supposed to be the giant killer, the plane that would make Boeing and Airbus nervous. It consumes 17% less fuel than the previous generation and has the most advanced fly-by-wire system in its class. But here is the mystery. Airlines are not buying it. While Airbus is celebrating hundreds of orders for its rival, the A380, the Embraer E2 is struggling to find a home. In the world of aviation, being the best doesn't always mean you win. Sometimes you can build the perfect machine, but the market simply refuses to take it. How can a plane that is so right be so wrong? Today we are going deep into the numbers. We are looking at why this tack shark is becoming a headache for investors instead of a gold mine. It's a story of great engines, bad timing, and very expensive legal trap. But first, hit the like and subscribe button. This simple action is vital for me. Thank you very much. The engine course: innovation versus reliability. To understand why the E2 is struggling, we have to look under the wings. This is the Pratt & Whitney GFT, the geared turbofan. It is a technical miracle, but for many airlines it has become a nightmare. Here is the simple science. In a normal jet engine, the fan and the turbine spin at the same speed. But in the GFT, there is a gearbox. This allows the big fan at the front to spin slower, while the turbine inside spins much faster. This makes the engine incredibly quiet and saves nearly 20% on fuel. For an airline, that sounds like a license to print money. But here is the catch. This technology is extremely complex. The gearbox and the new materials inside the engines are under massive heat and pressure. In the first years of operation, this engine started showing teething problems. We are talking about hardware failures, cooling issues, and parts that wear out much faster than expected. Normally, you fix a part and the plane flies again. But today, the global supply chain is broken. There aren't enough spare parts. Now let's look at the mass. In the first year of a new aircraft's life, you expect it to be in the air 10 or 12 hours a day. But many E2 operators found their planes stuck on the ground for months, waiting for engine repairs. If we compare the E2 to the older E1 during their first years, the dispatch reliability, which is how often the plane is ready to fly on time, was significantly lower for the new model. Airlines hate uncertainty. When a CEO looks at the E2, they don't just see a fuel-efficient jet, they see a risk. They ask, will this plane fly tomorrow, or will it sit in a hangar because of a broken gear? For many, the 20% fuel saving isn't worth a plane that cannot fly. The legal trap. How unions grounded a giant. But wait, if the engine is the only problem, Embraer could just fix it, right? Wrong. The biggest problem for the E2 is not mechanical. It is a legal trap called scope clauses. To understand this, we have to look at the United States, the biggest market for regional jets in the world. In the US, major airlines like United, Delta, and American don't fly their own small planes. Instead, they hire regional airlines to do it for them. But here is a very strict contrast between the big airlines and their pilot unions. This contrast is the scope clause. It says, you can use regional pilots, but only if the plane stays under a certain size and weight. There is one specific number that killed the E2. 76,000 pounds. That is the maximum takeoff weight, MTOW, allowed for regional jets in America. The older Embraer E175 fits this rule perfectly. It is the king of the US skies because it weighs exactly what the Union allows. But the new E175-E2, because of those big heavy fuel-efficient engines and those advanced wings, it weighs nearly 89,000 pounds. It sounds crazy, doesn't it? Embraer built a plane that is better, cleaner and more quiet. But because of a piece of paper signed by lawyers and unions, it is too heavy to fly in the US. The unions refuse to change the weight limit. They want to protect the jobs of pilots who fly the bigger mainline jets. They fear that if they allow heavier regional planes, the big airlines will stop using large jets and replace them with smaller ones. Embraer made a massive gamble. They believed the rules would change by the time the E2 was ready. They were wrong. The rules stayed the same. And now the E175-E2, the most important version of the plane, has 0 customers in the world's most profitable market. It is a tragedy of modern aviation. You can spend billions of dollars on engineering and create a masterpiece, but you can still be defeated by a single line of text in a legal contract. The shadow of Airbus, a David versus Goliath battle. Now imagine you are a CEO of a mid-sized airline. You need a new jet. You look at the Embraer E2, but then you look at its biggest rival, the Airbus A380. And this is where the shadow of the giant falls over Embraer. The A380 was not always an Airbus. It started as the Bombardier C series, a brilliant plane from Canada. But Bombardier almost went bankrupt building it. Airbus stepped in and used its massive global power to turn it into a superstar. How does Airbus win? It's simple. They are a one-stop shop. Airbus has deep pockets and a huge family of aircraft. When they talk to an airline like JetBlue or Delta, they don't just sell one plane. They can say, if you buy 50 of our big A321s, we will give you a massive discount on 20 small A220s. Embraer cannot do this. They are a smaller independent company. They have to make a profit on every single jet they sell. They cannot play the same money game as the giant like Airbus. The numbers tell a painful story. Airbus has over 800 orders for the A220. Embraer? They have around 200 for the E2. In the business world, success creates more success. Airlines see everyone else buying the A220, so they feel it is a safer investment. But there is one more secret weapon Airbus has – the pilots. If an airline already flies the Airbus A380, the most popular plane in the world, it is much easier to train their pilots to the A220. It feels like a part of the same family. If they buy the Embraer, they have to build a completely new department for training and maintenance. For many airlines, even if the Embraer is a slightly better technical machine, the Airbus is the better business decision. Embraer is fighting a war against a company that has more money, more influence, and a bigger family. It is a fight that is almost impossible to win. Global survival. Looking for a new home. So, is the E2 dead? Not exactly. Since the US market is blocked by legal rules and Europe is dominated by Airbus, Embraer is looking at the rest of the world. In places like Brazil, India, and Southeast Asia, the scope clause doesn't exist. These regions have thousands of islands and growing cities that need a plane exactly like the E2. Something bigger than a small turboprop, but smaller and cheaper to run than a massive Boeing 737. But the most important test is happening right now, in Canada, with Porter Airlines. Porter is the hero of the E2 story. They didn't just buy a few planes, they ordered up to 100 of them. They are using the E2 to fly long distances, like Toronto to Los Angeles or Florida. Porter is essentially a living laboratory. If Porter can prove that the E2 is reliable, that the engines stay healthy, and that passengers love the 2+2 seating, other airlines will stop being afraid. Porter is the advertising face that Embraer desperately needs. If Porter succeeds, the E2 survives. If Porter struggles, E2 may stay a niche aircraft forever. However, Embraer is smart. They are already preparing a plan B. They know the E2 might never be a global bestseller like the E1 was. So they are moving into a new space – sustainable aviation. While Boeing and Airbus are fighting over big jets, Embraer is designing a new generation of green planes. They are working on high-tech turboprops and even electric aircraft under their Energia project. Their strategy is simple. If you can't beat the giants in the jet market, lead the way in the green market. Embraer isn't giving up. They are looking for every gap in the market that the giants have missed. They are betting that the future of flying isn't just about being big. It's about being smart, efficient, and ready to pivot when the world changes. Now I want to ask you, would you prefer the Embraer E2 over Boeing or Airbus? And what do you think about this company in general? I'd be interested to hear your opinion. If you learned something new today, hitting the subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you next time. Look at this plane, the Boeing 777X. It is a masterpiece of engineering, with its massive folding wingtips and the largest jet engines in history. It was supposed to be the new king of the skies. It was built to replace the legendary 747 and change aviation forever. But there is a problem, a big one. Instead of carrying passengers around the world, these giants are sitting in a hangar, gathering dust. Why? Because in August 2024, the dream turned into a nightmare. It happened during a routine inspection. Engineers were checking the test planes after the flight in Hawaii. They weren't expecting to find anything serious, but then they saw it – a crack. This wasn't just a scratch on the paint. The crack was found in a critical part called the thrust link, a heavy metal component that helps attach those massive engines to the wing. Immediately, Boeing had to make a tough call. Ground the entire test fleet. No more flying, no more testing. Everything stopped. This isn't just another delay in a project that is already 5 years late. This is a major structural failure. So how did the most advanced plane in the world end up broken on the ground? Let's dive into the disaster. Anatomy of a breakdown. When you hear crack structure, you probably imagine a wing snapping in half like a dry twig. Thankfully, that is not what happened there. The carbon fiber wings themselves are fine. The problem is hidden under the wing, right where the engine connects to the plane. The broken part is called a thrust link. Think of it in this way. The engine is a monster that generates incredible power to pull the plane forward. It needs a very strong connection to transfer that power to the body of the aircraft. That connection is the thrust link. It acts like a massive titanium joint or a heavy-duty arm. Its only job is to push the plane throughout the air. So, here is the scary question. If this link breaks in the sky, does the engine fall off? The short answer is no. Aviation safety is built on a principle called redundancy. If one part fails, another part is ready to catch the load. The engine has multiple attachment points, so even with a snapped thrust link, the engine would stay on the wing and the pilots could land safely. But don't relax just yet. While the engine won't fall off, this is still a catastrophe for Boeing. Why? Because this is a brand new plane. Heavy metal parts usually crack after 20 years of flying, not during a few test flights. This is what engineers call a structural failure. It means the calculations were wrong. Either the metal material was too weak, or the vibrations from the engine were much stronger than Boeing expected. And you cannot fix bad mass with tape. You have to redesign the solution. The curse of GE9X engines. To understand why parts are cracking, we need to look at the beast causing all the stress. Meet the General Electric GE9X. This is not just an engine, it's a monster. It's officially the largest jet engine in history. To give you an idea of the scale, the front fan is so wide that you could fit the entire body of the Boeing 737 inside it. Yes, you heard that right. A whole other plane fits inside this engine. But is it possible to be too powerful? The problems with the GE9X didn't start in 2024. The curse began back in 2019, before the 777X even took its first flight. During ground testing, engineers noticed something alarming. The compressor blades inside the engines were wearing out incredibly fast. They were overheating and deteriorating. Essentially, the engine was hurting itself just by running. General Electric had to redesign these complex parts, which delayed the first flight for a long time. Now, seeing the structural cracks in 2024, it raises a difficult question. Is this engine simply too strong for the plane? It feels like the 777X is operating on the absolute edge of what is physically possible, and the stress is tearing it apart. Innovation or unnecessary risks. But the engine isn't the only thing pushing the limits of physics. Let's look at the wings. To make the 777X efficient, Boeing gave it a massive wingspan of over 71 meters. These long, slender wings are great for aerodynamics. They create amazing lift and save a lot of fuel. But there is a practical problem. The plane is simply too wide. It physically cannot fit into standard airport gates. So Boeing came up with a radical solution. They added a hinge. It is the first commercial jet in the world with folding wingtips. After the plane lands, the pilot flips a switch, and the ends of the wings, about 3.5 meters of them, fold up vertically. It looks like a transformer robot. This clever trick allows this giant to park in the same spots as smaller aircraft. It is an engineering marvel. But ask any mechanic, the more moving parts you have, the more things can break. This mechanism requires complex latches, locks and heavy pins to keep the wings straight during flight. If you look at the recent cracks in the engine mounts, you have to wonder about the wings too. By adding this folding system, did Boeing introduce yet another point of failure? It is a brilliant innovation, but in a project already plagued by structural issues, complexity is a dangerous game. The shadow of the predecessor. Now we have to address the elephant in the room, the ghost that haunts Boeing. When people hear about these problems, they immediately ask one question: is this the next 737 MAX? It is a fair question. The tragedies of the 737 MAX destroyed Boeing's reputation. People became afraid to fly. But it is important to understand that these are two very different situations. The 737 MAX disaster was caused by a software. A hidden computer program called MCAS pushed the plane's nose down, and pilots couldn't fight it. It was a digital trap. The 777X problem is different. It is not software, it is hardware. It is metal and physics. A structural failure like a cracked truss link is a classic mechanical issue. In a way, this is better, because you can see it, touch it and fix it, before anyone gets hurt. However, there is a deeper problem that links both planes: trust. The crack in the 777X was found after the plane had already flown for over 100 hours. Critics argue that this points to the same old problem at Boeing: a broken safety culture. Is the company still trying to rush production? Are they cutting corners to save money? When a passenger steps onto a plane, they don't care if the problem is software or hardware. They just want to know that the company built it right. And right now, Boeing is struggling to prove that they still know how to do that. The economics divide. While engineers try to fix the metal, Boeing's accountants are facing a different kind of a disaster. Time is money, and the 777X is burning billions of dollars. The airlines that ordered this plane are running out of patience. Take Emirates for example. They are the biggest customer for the 777X. Their president, Tim Clark, has been waiting for this jet since 2020. He isn't just annoyed, he is furious. He has openly criticized Boeing, calling the delays unacceptable. When your most loyal customers start shouting at you in public, you know you are in trouble. But the real danger isn't just angry words, it is the competition. While the 777X sits broken in a hangar, its rival is already flying high above it. The Airbus A380. The Airbus might be slightly smaller, but it has one huge advantage. It works. It is reliable, efficient, and available right now. Airlines hate uncertainty. They need to plan their schedules years in advance. Why would they wait for a maybe from Boeing when they can buy a guarantee from Airbus? If the 777X doesn't fly soon, it risks arriving at the party after everyone has already gone home. By 2027, will anyone still need this plane? Or will the Airbus A380 have already won the war? So the final question remains. When will you actually be able to buy a ticket? The original plan was 2020. That deadline is ancient history. Right now, the most optimistic forecast is 2027. And even that depends on how fast they can redesign the broken parts and convince the regulators. But when it finally arrives at your airport gate, should you be afraid to step inside? Here is the ironic truth. This disaster might actually make the plane safer. The FAA regulators are under immense pressure. They aren't going to sign any papers until they are 100% sure. They are watching Boeing like a hawk. Every crack, every vibration, and every bolt is being analyzed with a microscope. Because of these delays and failures, the 777X is going through the toughest certification process in aviation history. Paradoxically, by the time it carries passengers, it might be the most tested and verified aircraft ever built. It has the potential to be the safest king of the skies, if Boeing can survive long enough to finally get it off the ground. So, I have to ask, would you feel safe flying on the 777X in 2027? Or would you stick to Airbus? Let me know in the comments. If you enjoyed this video, please consider subscribing. This is a new channel, but I put a lot of effort into every video to make it clear, accurate, and worth your time. Now check out this video next. I think you will find it fascinating. Thanks for watching, and see you in the sky. In 2019, Airbus made one of the biggest announcements in aviation history. The production of the A380 Super Jumbo jet was finished. The market had clearly decided the huge 4-engine airplane was simply too expensive to operate. Airlines were choosing smaller, more efficient models. And yet, at the same moment, one of Asia's most respected carriers, All Nippon Airways, or ANA, was getting ready to introduce 3 brand new A380s into their fleet. Why? The decision immediately looked foolish. Leading airlines like Air France and Lufthansa were already retiring their A380s years earlier. The industry agreed that these planes were simply becoming too costly. This purchase went against everything ANA stood for. ANA is famous for efficiency. They were the launch customer and still operate the world's largest fleet of the fuel-efficient Boeing 787 Dreamliner. The A380 is the complete opposite. It is a massive aircraft with 4 engines, which means double of the maintenance and much higher fuel consumption compared to the twin-engine jets ANA allows. For a company focused on saving costs, committing over $1 billion to buy these gas-guzzling giants seemed like a terrible, simple mistake. But the decision was never really about the plane itself. It was about a secret, high-stakes battle for the most valuable asset in Japanese aviation. It was about making a calculated sacrifice to defeat a major American rival. The A380 was the price ANA had to pay. Fasten your seatbelt, check your like and subscription. Let's take off and find out. The ghost of Skymark Airlines. To truly understand ANA's strange purchase, we must first look at a smaller company, Skymark Airlines. Skymark was once the 3rd largest carrier in Japan. They tried to compete directly with giants like ANA and GAL. But they made one enormous, fatal gamble. Around 2010, Skymark placed an ambitious order for 6 Airbus A380s. This was a massive decision for a low-cost carrier, far too big for their financial stability. When Skymark couldn't afford the delivery payments and missed important deadlines, Airbus terminated the contract. This led to a huge penalty fee, in a range of $700 million. This fee, which Skymark simply couldn't pay, forced the airline to file for bankruptcy protection in January 2015. When an airline collapses, its most valuable assets are put on a market. For Skymark, the greatest prize wasn't the remains of its old fleet. It was the crucial landing and takeoff slot they controlled, especially at Tokyo's Haneda Airport. To explain the value, think of location. Haneda, HND, is only 14 kilometers from central Tokyo. Narita, NRT, the other major airport, is over 60 kilometers away. For a business traveler, the convenience of Haneda is priceless. Access to Haneda is strictly limited by the Japanese government. These slots cannot be bought or sold directly. For any airline, domestic or international, gaining a single slot at Haneda can unlock billions of yen in annual revenue. Skymark's bankruptcy suddenly put some of the most profitable aviation assets in all of Asia. These vital Haneda slots up for grabs. The battle for Haneda. When Skymark filed for bankruptcy, the fight for its assets quickly became a high-stakes proxy war. ANA had a plan to invest in Skymark, take control and integrate the valuable Haneda slots into its own network. However, ANA had a huge rival, Delta Airlines. Delta saw Skymark's collapse as a perfect opportunity to get a firm foothold in Tokyo. If Delta gained control, they could use Skymark's Haneda slots to launch direct, high-value routes to the United States. For Delta, this access would be an enormous strategic victory in Asia. For ANA, this was a disaster. If Delta got those slots, they would become a direct, powerful competitor right on ANA's doorstep, taking away premium passengers. ANA had to block Delta at any cost. The entire fate of Skymark was decided by a vote among its creditors. The largest shareholder was Interpid Aviation, which leased planes for Skymark. But the creditor with the single most powerful and complicated claim was Airbus. Airbus held a gigantic claim against Skymark, the massive penalty fee resulting from the cancelled A380 order. Because of the size of this debt, Airbus's vote was decisive in a bankruptcy proceeding. They could choose which airline's rescue plan to support, ANA's or Delta's. Airbus saw a chance to recover some of its pride and money after the A380 failure. They essentially delivered an ultimatum to ANA. We will vote against the Delta plan, ensuring you will win the Canada slots if and only if you agree to take over Skymark's cancelled order for the A380s. ANA didn't want the A380s, but they desperately needed the Canada slots and they had to stop Delta. So ANA was forced to agree to the deal, accepting the costly and difficult A380s as the ransom price for their most critical strategic asset. Lemons into lemonade. ANA was now stuck with 3 massive A380s they didn't want. The question was, what to do with planes that are too big and too expensive for your main business routes? The A380 simply wasn't the right fit for routes like Tokyo to London or New York. Those routes demand flexibility and frequent flights, which the efficient Boeing 787 and 777 provide. An A380 flight is too large. If a flight is cancelled or delayed, the airline suddenly has 520 passengers who need rebooking, causing a massive logistical problem. ANA had to find a route where the huge capacity was actually an advantage. The answer was Honolulu, Hawaii. Hawaii is the single most popular holiday destination for Japanese tourists. It is a market driven by seasonal peaks and large family groups. This route has historically been dominated by ANA's main rival, Japan Airlines, JAL. ANA realized they could use the A380's high capacity to flood the market, effectively lowering the price per seat and challenging JAL's monopoly. This decision was a strategic attack. Instead of matching JAL's frequency, ANA focused on matching their total volume with just one massive plane. To make the flight itself a unique product, ANA created the Flying Honu concept. They introduced 3 unique liveries, each painted with a different endangered sea turtle. This branding transformed the aircraft from a business problem into a family-friendly tourist attraction. Inside the plane, the layout was designed specifically for leisure travel. The cabin mix. ANA put only 520 seats on a plane, fewer than many competitors, to offer more space. Special features. They added the ANA coaches system in economy class, which allows a row of seats to be turned into a sofa for families. They also added economy class coaches and a premium economy section that was much larger than on other jets. By making the flight part of the holiday experience, ANA turned the difficult, oversized plane into a destination in itself. Was the price worth it? The ultimate question is simple. Did this crazy gamble pay off? Yes, it did. Before the pandemic hit, the A380 was immediately successful on the Honolulu route. The planes were popular with travelers and often flew with a load factor occupancy of over 90%, a huge success for such a large jet. More importantly, ANA achieved its main goal. It broke the dominance of its main rival, JAL. Before the A380, JAL controlled roughly 45% of the highly profitable Tokyo-Hawaii market. After ANA introduced its 3 A380s in 2019, ANA's market share quickly rose to over 40% in just 1 year. JAL lost a massive part of its revenue on that critical route. Let's look at the final numbers. The cost of the 3 A380s was roughly $1.3 billion at list price, a one-time expense. But the strategic asset ANA secured to Haneda Airport is expected to generate an estimated $500 million to $700 million in additional annual revenue for ANA across its entire network. The main lesson here is clear. A strategic asset is always more valuable than an efficient machine. The question was never about the operational cost of the plane, it was about the final price. ANA didn't buy these massive inefficient airplanes. ANA bought an estimated 500 million per year in permanent strategic advantage. They purchased the A380 as necessary entry fee to secure market dominance in Tokyo. What do you think about ANA's decision? I'd love to hear your thoughts in the comments. And if you like this video, consider subscribing. I'm just starting this channel, but I put a lot of effort into every video to make it clear, accurate and worth your time. And now let's meet in these videos. You definitely will find something interesting.